noise and signal to noise performance in any system, whether it's RF related or analog related, seems to bamboozle many people. Yet it's absolutely critical. When you're sitting there on your phone, can you hear me? Can you hear me now? Let me go outside. Come here. That's probably the most spoken word in cell phone dumb is, can you hear me now? And a lot of that is due to potentially poor signal-noise ratio because you're either in a shielded Faraday cage, such as the convention center, or you're in a place where you're on the fringe of the nearest tower. So understanding how to make signal noise improved is of critical importance. So what are some sources of electrical noise? Well, those of us that are familiar with particle beams the world, unfortunately, since the Big Bang, is a big entropy place, and entropy just gets larger. So there's charged particles that could be near each other, but they have nothing really to do with each other. Electrons are in motion, charges are in motion. When charges are in motion, they create electromagnetic waves that are potentially totally unrelated to anyone else, and that's something we call white noise, is because you have a pretty flat power spectral density where these things are radiating at all different frequencies at a pretty flat power level, and it's pervasive throughout the universe. So that's certainly one source of noise. Another source of noise could be a vacuum tube. Believe it or not, youngsters, vacuum tubes are still a very large part of your accelerators. I'm not sure that there's an accelerator on the planet that doesn't use a vacuum tube somewhere, whether it be people are probably not using, well, they're still using tetrodes and triodes. Certainly at Fermilab, the high power devices are of such a nature. And the way these things work is you got a filament that's burning incredibly hot. The filament in our Linac triode, which generates 5 megawatts of power, it runs at just a few volts, but about almost 7,000 amperes in order to keep the cathode toasty so that it can generate enough electrons to make 5 million watts every 15th of a second. Transistors, which are in every integrated circuit, even though probably nobody, I'll bet they don't even teach how to use transistors in electrical engineering anymore, which is, I don't know, anyone recently graduated as a double E? Yeah, did you take transistor course?
Yeah.
It wasn't required though, was it?
No, you had to take a
Oh, you had to take it?
course.
Okay, good, thank God.
The ECE 110 at U of I, you have to go to transistor.
Okay, excellent, because, I mean, that would be like, well, it'd be like software if you didn't understand that. It's like, well, here's a black box and it computes this for you. Just put a line of code in and you're done. Okay, no, you need to know how these devices work. And then, of course, the accelerator itself makes gobs of noise. My case in point is when I went first to work at Fermilab, my office was located right next to the Cockcroft wall. And not only did it sing at like 20 kilohertz, which my hearing was much better back in those days, used to drive me crazy. I had to put in curtains and all kinds of other stuff because at 20 kilohertz noise was killing me. But the thing would also arc over. The Cockcroft Walton was in a shielded environment and a dehumidified environment. But every so often, in the summer, because humidity is not as bad as it may be here on the East Coast, but it's pretty sticky in Chicago. And I'd be sitting, at the time I had, I was working on RF stuff, but I also had digital, circuits like, NAND gates, ECL or TTL and all that there, and I'd have them controlling whatever RF gizmo I was making, and then the Cockcroft Walton would go bang, bang, and then all of a sudden all my digital circuits would just, ding, and just reset. Okay, so that kind of noise is definitely very prevalent and can cause a huge amount of problems. And then finally, of course, in an accelerator environment, is we're forcing particles to collide with each other. And so, of course, you get all kinds of spray. This is an issue where the people who are actually making the detectors have got to be worried about it, because they're curious about every one of those squiggle lines and where things are going. So noise can come from so many different sources. Sometimes the noise is what we want to measure. Sometimes it's our photo, and that's what we're going to go through here.
Ralph,
Yeah.
that's signal you just showed.
That was really,
That's signal. That's not noise, that's signal.
yeah, no. Well, to you see. To you, that's signal. That's right. Well, that's what I said. Sometimes it's what you want to measure, and the noise is the signal. And if we talk a little bit about it, and we will be talking about stochastic cooling, the signal is noise, and we worried about stochastic cooling noise to thermal noise ratios. And I got a whole example of that coming up. Okay, so who are these noisy characters here? Because they're very important. Well, you got Mr. Boltzmann, and you got Mr. Kelvin, and Mr. Hertz. Okay? And the important thing to understand is noise comes in terms of power. Because if you take the units, volt and constants is watt seconds per degree K, and Mr. Kelvin developed the Ks himself. And Heinrich over there said, how often are you doing it? Every so many seconds, and we named it after him. And you add those whole things up, and of course you're left with watts. So noise is measured in watts, and it's in watts per unit bandwidth. So the more bandwidth you have, the more noise you have. You've already gone through enough spectrum analyzing to where if you saw your resolution bandwidth change, the noise floor went up and down, is because you're either integrating more or less noise. Okay, so units of watts, important. Oh, and then of course that is watt right there. Okay. So, this is where people start to get confused. And I'm going to try to deconfuse. Okay, the noise figure or factor, these two terms are used interchangeably. Some people like to think of the noise factor as a linear unit and noise figure as a dB unit. What you got to do is don't mix your dBs and linears, that's for sure. But be aware of that. And this calls the noise figure, noise factor. It basically describes how good a noise performance of a system is. And it's the signal to noise on the input divided by the signal to noise on the output. In my thesis advisor, it's the noise on the output referred to the input. Because if you end up taking a look at it, it's the noise on the output divided by the noise on the input. Now, if it's a perfectly linear amplifier, of course, the signal in is what it is, and the signal out should just be the gain times the signal in. Hopefully nobody's confused so far. All right? That's just what's supposed to happen. Now, another way of looking at it is you've got noise in, you got noise added, and then you got noise out, coming out of the device. Okay, there we have noise on the output divided by noise on the input plus the gain factor in there. Okay. So now, if I have a perfect gain box, perfect meaning it just amplifies the signal but adds no noise whatsoever, well then of course the noise on the output is equal, the noise figure here is the noise out divided by the gain times the noise in. And because nothing has been added by this amplifier, it has a noise factor of 1 in linear units, or a 0 dB noise figure in dB units. The perfect amplifier. The perfect amplifier has yet to be invented, but getting pretty darn close. Okay, so the noise in is KTB, we've established that. And the noise out is the noise in times the gain, plus whatever the amplifier added to it. Yes?
So this noise figure seems to be dependent on the amount of noise you put into the amplifier.
No, it's the ratio of the output signal noise ratio, input signal noise ratio to the output signal noise ratio.
How do you know if I increase the noise
Okay.
twice?
Good question. You're leading me into the rest of the talk. Okay, noise out is noise in times gain plus whatever noise gets added. So I can rearrange this now. This is simple algebra at this point here. Is noise added then has got to be equal noise out minus noise in times gain. You see that? I didn't do anything but rearrange terms. Okay. And I can rearrange that too, because now I can put the old noise factor in, which we already know what that is from the previous slide. And we just keep on doing the appropriate substitution. And now I've got this equation here that says the noise added is equal to the noise factor minus 1 times KTBG. Okay, you can look over this again yourself, but I've done nothing terrible, no differential equations or anything yet. This is just simple mathematics to get to this point. This, of course, when I'm doing any kind of a multiplication, I'm talking about the linear units. That's the one thing. Do not confuse, while we may measure things in dB, when we start doing our calculations, you'll do calculations with linear things. dBs are nice for engineers to think of because it allows me to have such a large dynamic range at my brain tips. But when you're doing calculations, do not mix nonlinear and linear terms. And you've had to come across that somewhere else in your life, like your checkbook. Okay, so there's another way of looking at things. It is called the effective noise temperature. And the effective noise temperature is the T. most people in the world have, that T in KTB is, it's taken as some T0. And T0 is room temperature, not this room. For me, this room is too warm. I keep asking to make it cooler. Hey, the toys have arrived. Yippee. Yeah. Thank you. Just about the way I thought it would. Okay, yipes. Okay, so who would care about? See, normally T0 is 290 degrees Kelvin, and 290 degrees Kelvin is like, I don't know, 68 or 70 degrees, you know, comfortable room temperature for human beings. The thing is, we don't always work in this kind of environment. Anybody who's worked with radio astronomy, of course, knows that they tend to cool their amplifiers on their front end. Why? It's because the noise is KTB. I can't touch Mr. Boltzmann. I can't touch the bandwidth if I want a certain amount of information. So the only thing I have control over is temperature. So you'll see a lot of astronomy things as the antenna amplifier is cooled to potentially cryogenic amplifiers. Also true in accelerator physics. When we're doing stochastic cooling, we have a noise-to-noise ratio. The particles going around the ring were, you know, antiparticles. And again, if I just had one particle in the machine, every time it would come underneath an antenna, it would create a delta function. It's almost the perfect, ideal delta function. And if I start putting more and more of them in there, I get a family of delta functions which starts to show like a spread of energy at those revolution harmonics, which I showed in a lecture previously. And that's the noise that I want to work with, and not all the thermal noise that's coming out of the amplifier or the back terminations on the antenna. And so you make things cold, and now you have that one control. And if you need to do something fast, you need a lot of bandwidth. So these are limitations. The example I'm coming up with will show all of this. So many situations you will deal in effective noise temperature. And now, of course, the beauty of an effective noise temperature is there you can just add the temperatures. If I have an antenna that has a temperature of 25 degrees Kelvin, followed by an amplifier of 25 degrees Kelvin, the noise temperature of the system is 50 degrees Kelvin. Okay, so that makes, and so that's just an easier way of dealing with things when you're not operating at T0 of 290 Kelvin. Okay, so where's the noise floor? People may have heard this. It's temperature dependent, and noise energy is in joules, which is watt seconds. And here's this magic number and where it comes from. It's not a mystery. So I just take K times T, where if T is equal to 290 degrees Kelvin, that's 4 10 to the minus 121 joules, which is 4 times 10 to the minus 18 milliwatt seconds, which is minus 174 dBm per hertz. Pretty much every engineer has this noise floor memorized in their brains. And now the reason it's nice about having an understanding of dBm per hertz, everything is normalized to 1 hertz. If I could have anything this good, and I had a system bandwidth of a megahertz, well, a megahertz is 10 to the 6th, so that says my perfect noise floor would be 60 dB hardness or minus 114 dB hertz. And that's the nice thing about doing things like this in your head.
So if I see on my instrument that the noise floor is minus 200, it's something wrong with it.
There's something wrong with you. It's one of two. There's no way in the world you're going to see that on your instrument, unless, of course, your instrument's operating at some cryogenic value. Okay, the noise. This is only the noise floor for room temperature. Okay, there's a different noise floor at every temperature, but this is a number that most microwave engineers know by heart. Okay, and here I just said that is if you have a megahertz bandwidth, you just add the dBs, which is very convenient. Okay, so now we have a reasonable understanding of what noise is, but how do we measure it? Because that's what you spend the money on, is a very good noise amplifier. So here's the same thing that we have. There's some input impedance at some temperature. There's an excess noise source. I have brought 3 excess noise sources with us, so we can have multiple experiments at once. This is an old Hewlett-Packard one, and these 2 are from a noise company called Micronetics. On one end, there's a BNC connector. That's what powers it, and I think they're all at 28 volts. It says right on there, 28 volts. And what that does is bias a diode in here and heats up the junction of a precisely made diode. And then, after the diode, is a significant attenuator that when this thing is on or off, it always looks like 50 ohms looking into here. So when you turn it on, it has something called an excess noise ratio. And the excess noise ratio, and this one is printed as a function of frequency. In this one here, I just have it, well, this one has it as a function of frequency. This one broke a number of years ago, but I recalibrated it against these guys. And I just have a value on there of 12.1 dB at 1.5 gigahertz. So what you're gonna come up with here, as a matter of fact, if you measured an amplifier with all three of these, and maybe someone will have the motivation to do that, it'll be interesting to see how close these excess noise ratios are to what they say they are. Because these have been around for a very long time, and I have not had them go back for any kind of a NIST calibration. Okay, so under this condition, I have an excess noise source, which I now know what its value is, and as I said, don't trust anybody. Well, trust me on this one here. Make believe I just got this back from NIST, and I'm telling you that this is what it is. You're saying no, but that's okay. What you can do is, if you did the experiment I just told you about doing the same amplifier with all three noise sources, we'll narrow it down as to who these guys really are. Hopefully, you get at least 2 to 3 to tell you the same answer. Someone's got to do that before we're out of here. Okay, so now I'm starting to look at this, and this is the way Adams performs the analysis in the Adams book that was one of our references for you. So with the excess noise off, okay, all you have is whatever noise comes out of the with the device, the DUT, and the noise on the input times the gain. We're assuming this thing has gain, but it could have loss. It could have loss. We'll talk about that in a little bit too. And then I have a detector out here. The detector could be a precisely tuned receiver, which in our case happens to be a spectrum analyzer. And a spectrum analyzer has very good performance, and with the gain of the amplifier, should put a signal above the noise floor of the amplifier. So one of the things I believe was in the introductory thing, you're supposed to measure the noise floor of the amplifier and look at it as a function of resolution bandwidth, right? Okay, so you already know a little bit about the amplifier. And then when I turn the noise source on, I have 3 sources of noise: the excess noise times the gain, the device noise itself, and then the noise on the input that's excess times the gain. And that's this noise number 2. Okay, so now I can actually, at some point then, take, now this is looking ugly, but it's really not ugly at all. So I take noise 2 over noise 1, and there's a lot of KTBs and Ts and everything else in here, but if you go through the algebra, you'll end up finding out presto chango, and I encourage you to do that, because you'll see there, you can factor a lot of things out, and you've got that N2 over N1 is Y. It turns into the noise factor is the excess noise ratio times 1 over this thing called the Y factor. Everyone, why it's Y, I don't know why. It's just arbitrarily chosen, and everyone has had that for at least the 35, 40 years that I've been in this business. And we are going to measure that Y factor, because on the spectrum analyzer, you can store one trace with the amplifier, with the noise source off, store it, and then you can get the other trace with the noise source on, and you'll want to average it because it's going to look noisy, average it, smooth it, and then you'll, at the same exact frequency of the markers, take the difference, and it's going to spit out the noise factor in dB, because the spectrum analyzer is talking dB. But when you're doing your mathematics, remember to convert the dB to linear. Okay, so now we're again going to do the measurements. And there are certain things that, because you do know the excess noise, you can read through the whole equation. And the noise figure in dB is going to be nothing more than the excess noise ratio, which we're taking as printed on the device, minus 10 times the log of N2 over N1 minus 1. And I encourage you to do the algebra in order to be able to do this. Now, does this end up making a real lot of sense? I come up with the analogy is, if I was in a football stadium, that's my amplifier. And it depends on if you're at the Seahawks next in 2 weeks. They say they make the most noise of anybody. Is that the team that makes the most noise of anybody? Like 142 decibels or something of that nature? And then, of course, I come out to the middle of the field and I start going, you know, you can hear me above all of that other crap? Okay, the noisy amplifier are those Seattle fans, and then me, a lone Bear fan, comes in and sits on the, you're not going to hear me at all. So the excess noise ratio there is going to be dribbled. To be absolutely dribbled. Why? Because that stadium is a lousy noise source. Or it's a good noise source. For our purposes, it's a lousy noise source. Unless, of course, the Bears were in the playoffs, and then it would be a good noise source. But if that stadium just had two of us on the court, on the field, and we were both yelling, you'd be able to hear us probably independently, because now the separation between the noise added is just the two of us. Right? So when you have this excess noise source, if I turn the excess noise source on and the noise really goes up on the output, that's because there's just two of us on the field. Whereas if it goes up very little, that means all the noise I added on the input with the gain didn't measure a hill of beans compared to all the noise coming from the rest of the stadium. And that's how we're able to measure this ratio, which is going to tell us how good the amplifier is. Okay, I showed you what the noise dials can look like. The way we used to do it, and this was the precise way. We actually, when we were doing stochastic cooling in the early days, we never trusted these. These are kind of expensive. You know, maybe today they're in the $1,000 department or something like that. But we didn't trust them because they don't tell you exactly. They skip, 1 gigahertz it does this, 2 gigahertz it does this, 10 gigahertz it does this. Well, what if we wanted to know what it was at 1.5? Well, you can sit there and interpolate and the like. And the differences here are only a few tenths of a dB. Okay, but as you start to get a very low noise figure amplifier, every a 1 dB noise figure is equivalent to 77 degrees Kelvin, essentially liquid nitrogen temperatures, and it's almost linear down to 0 Kelvin. So every tenth of a dB. Now you guys have been measuring things. You've probably seen ripples of a tenth of dB on everything, and a tenth of a dB is about 2% error. And again, if you're willing to take a 2% cut in your pay without feeding it, well, you're a very happy person, and that's all I can say. But as you get to these lower and lower noises, and you want to get to the lowest noise possible, every tenth of a dB is a big deal. So what we would use instead of these things is we had hot and cold running noise over here. And you can buy these things, and it's a very simple device in that there's a precisely controlled oven in one chamber with a 50 ohm terminator in it, a very high quality 50 ohm terminator, and the oven is controlled to a fraction of a degree. So you know what T is very accurately. And then the other half has a dewar in it, and you fill that with liquid nitrogen, and that has a very precise value of 77 Kelvin, but it depends on the atmospheric pressure. So if you're wanting to be really good, and we measured amplifiers with noise temperatures in the 10 to 15 degree Kelvin range. And so now you're starting to think of, I really need to know that delta T, because the delta T there, of course, is the excess noise ratio. And you would sit there and if you were making the measurement on the top, say at Los Alamos, where you're at 7,200 feet or whatever, the temperature of liquid nitrogen there is different than it is at 700 feet in Chicago. And that means the temperature is going to be different. And now, a few degrees Kelvin temperature noise performance doesn't sound like a big deal, but if you're operating down at 7 to 12 degrees Kelvin, it's a huge percentage error. And you'll see an example coming up on how important this is. So we would have hot and cold running noise, and you'd have to keep the dewar filled to a certain amount. You had to let the oven stay on for an hour or two to get totally stabilized, and you could make the excess noise ratio. And back when we were doing it, it took a lot more equipment than it would today. Some of these very amplifiers could even be on the table here today. We don't know. This is an old picture. Here's our old network analyzer, half a rack, not including the computer. This was one of the very first automated network analyzers that Hewlett Packard ever made. And I think we bought two of them right off the bat, about $110,000 in 1980 or something like that. Here's a refrigerator where we put the amplifiers on. It's a helium compressor refrigerator. We were able to get the amplifiers down even as cold as maybe 20 Kelvin. We couldn't go to liquid helium with this, but we would measure them, and there's a hot and cold noise source. This is the receiver we used. We didn't use a spectrum analyzer back then. We used a fixed tune receiver that was part of the noise kit. And here's our local oscillator. And we measured hundreds of amplifiers and short samples before we ended up buying the mass quantities that we needed. Okay, so now, that was one amplifier. What happens if you have a real system, which is more than just a single device? And here I just look at it as a three-stage system. And so now that's going to have a different noise performance than a single system. And every stage is going to have its own gain and its own noise figure. So the noise figure for the system is the noise out divided by the noise in times all three gains. And of course, we have to expand that, and I encourage you to do so. And it looks ugly, but it's not so bad, really. All of these terms cancel. And what you end up with is the noise figure of the system is the noise figure of the first stage, plus the noise figure of the second stage minus 1 divided by the gain of the first stage, plus the noise figure of the third stage minus 1 divided by the gain of the gain multiplied in both stages. So all of a sudden, if that first thing is amplifier with a gain of 30 dB, that's a factor of 1,000. That says this contribution is going to get divided by a factor of 1,000. So even if the noise figure of stages 2 is lousy, its contribution is going to be 0.1%. Now this could be maybe be your amplifier that drives the kicker, that generates hundreds of watts or thousands of watts, and it has a lousy noise figure of maybe 10 to 100 or something like that. But now it could have a gain of 30 dB too, and then it's going to be divided by 30 dB plus 30 dB, a factor of 1,000,000. So this tells you right off the bat that your preamplifier sets the signal noise ratio of whatever system you're building. And that's where you want to start investing your money. Okay, so what do? You put, did I miss a slide? Okay, so you can also do the exact same thing with effective temperature. The effective temperature of the first stage, second stage divided gain of 1. These are all equivalent things depending on if you're not working at T0. Like I said, we would work in effective temperatures all the time for stochastic cooling. Because when I'm talking temperature, it's definite. As opposed to if I say a 3 dB noise figure, 3 dB noise figure means its effective temperature is 290 degrees Kelvin. It's double the input room temperature.
Is that down TE3 at the end?
What's that? Oh yeah, it should be TE3, yeah, mistake, good boy. Okay, so where do you put your antenna? At home, you put your amplifier right on the antenna, and most things, if anyone still has something that doesn't have cable, me, I got rid of cable several years ago. I have an antenna on the roof that has a preamplifier right on the beast. Now that sets the signal noise, so even if I have a dB or 2 insertion loss on the cable going down, that's not going to affect my signal noise ratio too much. Okay, and of course when you go to the airport, you see that little goozy thing there on the radar system. That's the preamplifier in order to make sure the signal gets to the control tower without too much fuzz on it. All right, so remember, if I had a box with a very long cable terminated, or just a resistor in there, and I put my network analyzer on there, and of course the connectors are all really good, so there's really no mismatch. We're talking an ideal type situation. When I looked inside of these things, they both look the same. They both look exactly the same. They look like a 50 ohm termination. You don't necessarily know otherwise. Okay, so now let's talk about building a system. Here's a stochastic cooling system where there was a pickup, and there was a coax to go from the pickup to the preamp, and then of course the preamp had to eventually drive a kicker amplifier, and then it goes to the kicker. And of course the beam goes round and round, and the music comes out here. So let's assign some numbers here now. It's an itsy-bitsy signal on the input. Remember, it's just a very small number of particles circulating at the revolution frequency, and when you integrate the whole batch of them, it's about a minus 80 dBm signal going into it. And that's 10 to the minus 11 watts. Very small number. Now, the whole thing here is the design of the feedback system. When you throw all this in and you simulate it, it says, I need to develop 100 watts of signal on the kicker. Because if I don't have 100 watts of signal on the kicker, I'm not going to have enough system loop gain to perform the cooling as fast as I would like it to be. So that's my specification that I've got to be able to hit. But the question is, can I do it? So now that says I need plus 50 dBm of watts coming out. So I'm just going to look at that very simply and say, that's pretty easy. All I got to do is come up with 130 dB of gain, right? Not a problem. And of course, the neophyte engineer may say that to his boss. If it was me, I would laugh at you, because that's not what you can do. Okay, so now let's go a little bit further. Now we're going to add that first stage, it's not an amplifier anymore, it's a coax, but it's a device. And it has insertion loss. Doesn't have gain. So that's interesting. And we're going to say that it has an insertion loss of minus 1 dB. which is an attenuation of 1 dB. And an attenuator has a noise figure exactly equal to its insertion loss, 1 dB. The amplifier has got a noise figure of 3 dB, which is equal to 2, but it has a gain of 30, which is 30 dB, which is a gain of 1,000. Okay? And then over here we have the kicker amplifier, which maybe has only, it has a gain of 100, which is actually maybe a bunch of amplifiers in a row. I just lump it into a box. And it has a noise figure of 10 dB, which is equal to 10, and that's 10 to the 10th. So I'm adding that up. There's my 130 dB of gain, which is really 129 dB of gain because of the loss of the cable. So my noise figure of the system at that point there is going to be 1.25, because 1 dB noise figure is 1.25 linear. And at this point here, now you can see that the noise figure has gone up to 4 because the loss adds directly to the preamp, and that's a noise figure of 1.25 plus the first stage minus 1 divided by the gain. Gain is now 0.795 because it's loss. Okay? And then over here, after we come out the other end, we end up having a total noise figure of a little over 4 dB. You'll notice that even though that's got a huge thing, it's being divided by essentially 29 dB, which is now making the whole noise in the system 2.52, okay? Which is worse than the preamp. And go another step further is what do we have under those situations now? Is we still have minus 80 dBm of signal. The system bandwidth is 1 gigahertz. So now we can calculate what the noise is in 1 gigahertz. And in 1 gigahertz, at room temperature, that's minus 84 dBm of noise in that front end signal. Unfortunately, when I go through that coax, noise lost is just noise regenerated by the electrons in the cable and propagating. Whether it's a long cable or if it's a 50 ohm terminator, a resistive loss still has a noise factor of the minus 174 dBm per hertz times the bandwidth. So the noise stays the same because the noise just propagates and is regenerated in the lossy device. But we did lose a signal, a dB of signal noise ratio. Now we come over here and go through a 3 dB noise figure. All of a sudden the signal noise ratio has gone to 1, which is 0 dB. And now we're going to go through the amplifier and adding the amplifier. So now I end up here in this situation. I get 158 watts out, okay, but I only get 79 watts of signal and 79 watts of noise. I got to pay for all of those watts, whether they're noise watts or good watts. And that's not going to make it work because I'm short. Okay, I've got to come up with something a little bit extra. So you go back to the drawing board. You don't go out and buy that system. It's time to come up with a better design. And now what I say is, well, let's buy a better preamp. It's going to cost a little bit more money, but if I buy a better preamp, I have the exact same thing on the front end, the same coax, but now I'm buying a much better amplifier, which has a 1 dB noise figure. And that's a very possible solution. I go through the whole thing again here, and now I still have the 79 watts of noise, but because that amplifier is better, I'm down to 50 watts of noise. Still not the 100 watts that the system needs to have the right transfer function to make the cooling work properly. So we go to one more case and say like, okay, it's time to bite the bullet. We can't really buy a much better noise amplifier than 1 dB at the time. You can these days, but not terribly much better. So what we decided to do is get the refrigerators out. And because the pickups are terminated with resistors, they're matched transmission lines, is we can now make T equal to 80 Kelvin instead of 290 Kelvin. And that changes the signal noise ratio right off the bat, because the signal is still minus 80 dBm. The same number of particles are going through this piece, and that's the energy they deposit in the impedance of the antenna. But the signal noise ratio is now going up to 9.6 dB. You get rid of the cable. And how do you get rid of the cable? You put the preamp inside the pickup at super cold temperatures. So now your temperature of the amplifier can end up getting colder. Okay, I mean, it gets to be 1 dB when it's cold in this particular case. And then voila, the same power kicker amp, and now you finally have gotten to the point where you've generated 100 watts by just changing the system design. Okay, well, that doesn't come for free. This case one was, I have a warm pickup, and I have a not so good amplifier, and I don't get what I really need, so I can add more gain on the output to get I need 26 times more to get to 200 watts, so I have 100 watts of signal, and say the power cost is $100 per watt, that first system, say, could cost, without all the refrigerator, I mean, this is just the RF microwave system, it costs $20,000-ish, say. I go to the second system now, and doing nothing more than buying a better preamp, the cost actually goes down and the performance goes up. That could be good enough. That's all a function of figuring it out amongst the team to see what's really good. Then, of course, the last one could be pretty expensive, because now maybe I need a $50,000 refrigerator just to cool the front end. We're not doing a superconducting cavity here or something like that. And the preamp cost is going up a factor of 4 in cost. And the power cost has gone down even further because now there's more signal and less noise coming out, but the overall cost is more. So it's trade-offs. You're going to find that you have to do trade-offs at all times. Since we did this first upgrade, we actually found that when we did our next upgrade in the debuncher, we had to go to liquid helium. And it really adds cost to go from 80 Kelvin down to 4. But it was the only way that we could increase the cooling time to get the signal noise what we needed. So you make that pitch. Dave and I made that pitch. We worked on that project. That was about a $10 million upgrade. And he designed the pickups, I designed the RF system, and we totally gutted the P-bar source in 2 areas. And our lives were on the line. It was a tense period, but it worked just nice. Okay, so here's what happens on that front end is here's a custom hybrid that we made, and I have a version of that here, this thing. It's something that Fermilab got a patent on many years ago. We call it a Petter hybrid because Jeff Petter was the engineer who designed it. Very novel idea, an incredible common mode rejection. You'll see that when you measure that in the lab. And that's this B sitting here. And we have injection ports so that we can test things. Here are these 2 little postage stamp amplifiers, kind of similar to this little guy. And this whole thing is sitting at about 4 to 5 Kelvin. And you'll notice that the coax lines going in and out are all stainless steel. Because now you have a little bit of a battle between the cryogenics guys and us stochastic cooling guys, is they said, we would like these to be 10 feet long because we don't want the heat leak of a 5-degree Kelvin coming out to the outside world. And we said they can't be that long because in stochastic cooling, you have to take the signal and get it to the kicker by crossing the ring and timing it to within picoseconds. I don't have those extra nanoseconds to waste. So we compromised on just getting 1 zigzag to the outside world, and you use stainless because stainless is a lousy thermal conductor. The center conductor is copper, but it's much smaller, and he's even silver plated to improve that. But the stainless does a terrible job of conducting heat, and it's copper plated on the inside. So that's a compromise there, and that stuff's like $20 a foot when you need it. But this whole front end, then, we were able to make the noise performance of those debuncher systems were anywhere from effective temperature of 15 to 25 Kelvin. Okay, but there's other restrictions. What happens if your kicker happens to be a ferrite or something? You can't just indiscriminately pour more power into it. The first couple of cases, I didn't get 100 watts, and I could say, yeah, just buy more watts, and you'll get the signal. But the thing is, you might end up saturating your ferrites, in which case that kicker won't work very well. So that's not a possibility. There could be a situation that maybe my kicker can't handle the power, period, and I zorch it, so I can't indiscriminately increase the power, because that's not a possibility. And then the other thing is, a lot of times happens, there's no room to put more kickers in because the lattice is full of all kinds of other stuff. And that's why you have to chase all these other possibilities to see what will actually work for your particular application. Okay, so again, the noise basics is the minus 174 dBm per hertz. I've asked, I believe, in the first Get to Know Your Network Spectrum Analyzer for you to tell me what the noise floor is of the analyzer. And one of the questions will be, how good is the noise figure of the spectrum analyzer? Because these are really expensive, nifty things, but you're going to tell me what the noise figure is of the spectrum analyzer, and you're going to be surprised. Because we now can measure the displayed noise floor with no input, put an determination on it, and then you can find out what the dBm per hertz is. And that'll tell me a lot about what's going on. Okay? You'll see this is an older version, but the noise floor typically creeps up as this is going up to 22 gigahertz here. A lot of times you'll see on any of these really wideband spectrum analyzers, the noise floor creeps up. And as you go higher in frequency, getting low noise performance out of the mixers and amplifiers becomes more difficult to actually implement. So you'll see things like that. You can measure noise on some other things. This is a project we had where we're using a laser diode as a optical amplifier. It was a 1300 nanometer optical amplifier, which is essentially a laser below threshold. It has no mirrors on the end, so the incoming light gets stimulated and amplifies it. But this is pure noise. I mean, a laser below threshold is a very noisy environment, as you can imagine. And depending on how I bias, this is an optical spectrum, so now you can see that this is in nanometers, but depending on how I bias it, I can immensely change the noise performance. And again, here it's 5 dB per division, so just doubling the current, I can have 10 times as much noise in this thing. Is that tolerable? Depends on the application. Okay. We need to understand certain things about synchronous phase and phase stability. This slide will come up again when I talk about RF type stuff. The only reason this guy stays exact where he is because he's in phase synchronous. If he was doing a synchrotron oscillation, he'd be going, and at some point he'd be running out of room to do that. Now, it looks like a pretty nice pure sine wave there for him to slide down. But then there's something called phase noise, which we can also measure here for the student who is fully engaged. Is phase noise varies depending on how clean the thing generating your sine wave is. And this is just a spectrum of several different noise performances of amplifiers. And phase noise is that little minute jitter that happens right close to the carrier, out to maybe say even a megahertz. When you're, for instance, I showed this in the talk where we were discussing those Schottky signals from the Tevatron, is you can see here now, this is 10 dB per division. So there's some variations of 10, 20, 30 dB in just this garbly, undesired noise coming out of your signal generator as a function of frequency. And what this is caused by could be power supply jitter, it could be the fact that maybe there's not that very good filtering in the resonant circuit that's generating the sine wave. And the thing is, if you'll know, if this is a radio, of course, what we hear over here is all in the kilohertz regime. And that says that if my weak signal is down here someplace and I'm using this as my local oscillator, when I down convert it and try to detect it, I'm going to hear absolutely nothing because the phase noise of the thing I'm using to convert it is larger than my signal information. So we'll have the opportunity to measure phase. I know some of these Roden Schwartz guys have got a phase noise built-in thing under, and we could actually measure the phase noise of various amplifiers. Someone gets ambitious. Okay, phase noise, noise can also come in the form of intermodulation distortion. This was a big deal, especially for the stochastic cooling stuff. It's tough to see this little thing, but what this is a notch filter, and I think this one's a notch filter. I can't remember. We'll find out when we measure it. But we wanted to find out. Remember when I talked about when we have mixing products and the even products go out, but all the odd products come back in? Well, when you have a broadband system, which is what the stochastic cooling was, they're like octave wide, and it's basically the spectrum is noise. I mean, the Schottky signal coming from the beam is noise. It's periodic. You see the revolution lines and all of that. But it's all of these frequencies now multiplying against each other back and forth. And what this shows is all the odd intermodulation products come in and fill in this notch. So there's a TWT amplifier over here, which can become a very nonlinear thing, and each one of these things is a different power level. So we really wanted to notch out some of the noise, and this is how we qualified the traveling wave tubes that we bought, is we wanted to understand their nonlinear characteristics. And it's not the same as just doing a two-tone intermodulation measurement, because of course we're interested in thousands of frequencies that are inside this bandwidth. As I change the power level, all the odd harmonics are starting to fill in this notch. So you can see, this is what, 5 dB per division, 5, 10, 15, 20, 25, 30. So the notch is 40-ish or something dB deep with very low powers, but it's barely 15 dB deep if I'm up at high power. That says that I may not be able to run this amplifier at the 160 watts because the thing I want to not mix back in and cause an error signal has got to be at least 20 dB down. And so here you have to buy a 200 watt traveling wave tube, but you may have to operate it at only 40 watts. And that's several $100s a watt. And so now the cost of your RF system goes up. And you have to convince the people who have the books that don't know squat about RF You have to tell them, hey, look, here it is. You want it to work. This is not fiction. Here's some Schottky signals in the Tevatron. Those little bumplets on the side of the Betatron sidebands, those are the ones that we want to act on. And unfortunately, there's this monster coherence signal there. So the system has to have an enormous instantaneous dynamic range so that the big system doesn't saturate and start creating more intermodulation products that could hurt this. This was a tough nut to crack. This was bunch beam cooling we tried in the Tevatron. So here, after the pickup, you can actually, this was an easy measurement to make, because before we had our coalescing down, coalescing was basically taking a bunch of bunches and putting them all into one bucket. That didn't work so good in the early days, so this was just an interesting thing to measure, is that's one beam batch, and here's the other beam batch, they're 18 nanoseconds apart, and that's right after the pickup. And here you can almost see that bucket to bucket is about a factor of 2 to 1 in terms of the voltage. This is looking at one of these fast digitizing scopes before we had the analog one. This was back in the mid-1990s. We used a sampling scope to do this. After the preamp, you can already see, because that coherence spike was so large compared to the little guys, is that we've already hit saturation on that first bunch, okay? And the ratio here is no longer preserved. Why? Because we've added all kinds of noise in or intermodulation products by saturating the amplifier. Finally, after coming out of the power amplifier at the end, what do you see? Nothing, you know, so that's a real problem. Now there's a way you can fix that too, all right? Here's looking at that same signal if you had, the particle beam was going around in some discrete bunches. And when the Tevatron was running, we had initially 3 and then 6 and then finally 36 bunches. But the machine has the capability of having over 1,100 bunches in it. But when the beam is not underneath the pickup, why listen? Because only thing that's there is noise. So what you can do is you can do some gating. And because you know exactly where the beam is at all times, you can apply a beam time gate with some nice fast switches, and all of a sudden this horrid signal turns into this where you can actually see it. So that's another way you can manipulate the signal noise ratio. If you have a bunched structure in your particle accelerator, you don't need to look all the time. You can, and another nice feature of this is that, of course, you can actually open the gate and look at any single bunch. If the machine was full of bunches, you can gate around any individual bunch, and you can measure characteristics of one bunch versus another. Or what we did in the Schottky system in the Tevatron is we could see the beam tune shift variation between the first bunch in a batch and the last bunch in a batch. And that could be worked on to be corrected. So you can learn an enormous amount of stuff from the Schottky signals in the machine. Okay, and then finally, just looking at what the dynamic range is of something. The boxes here all say don't put in more than 1 watt, and that's 1 watt at one frequency because bad things will happen. But the same token is, if you have a broadband system, 1 watt is the integral of everything into bandwidth. And if that amounts to 1 watt, that's really bad. So if you're looking at something in a single tone, well, I may have a very large dynamic range because I'm in a narrow band system. But as the bands get to be wider, all of a sudden, my dynamic range between the noise floor and the maximum signal I can put in becomes very limited. You'll find this to be true in any amplification system. It's especially notable if any of you guys have seen optical links are very popular now because you can transmit gigahertz of data on an optical link. But again, the laser has a certain saturation value, and what happens is exactly this. I can use the very many gigahertz bandwidth of the laser in the optical link, but now the power spectral density per unit hertz has got to be distributed amongst the whole bandwidth. So that means the signal to noise ratio goes down for every individual bit of information in that bandwidth. And so now instead of having maybe a 50, 60 dB, 100 dB dynamic range in an optical link, you end up with only 30 or 40. Is because you're trying to put so much information on the same link. Is that adequate? It depends on the application. And in our case, when we're doing stochastic cooling in the recycler, in order to get the signal from one end to the other, I couldn't go on a piece of coax, because the piece of coax would have been 2,000 feet long. And I wanted to use gigahertzes, so that meant I could use at maximum a half-inch coax. And the insertion loss of 2,000 feet of coax, which you can go on that graph I showed yesterday, is such that the signal noise ratio going out would be lousy. There'd be no signal coming out whatsoever. So totally useful. I can't do that. I can't send the signal across the ring on a fiber. Why? Because the fiber only goes 70% the speed of light, and I've got to meet the beam on the other side to a few picoseconds. So the only way I could get it there is I had to send it through free space. on a laser. So I took the information from the pickup, amplify it with good low noise amplifiers, get it up to a decent signal noise ratio, enough to drive the laser to get the maximum out of its dynamic range, put it on a couple of telescopes, shot it 2,000 feet through a vacuum, 2,000 foot long sewer pipe that we pulled a vacuum on. On the other side was a photodiode that collected the light, and we had piezoelectric mirrors on this side, which these guys know very well. There's like a little bit of a video game steering to get it right on the laser receiver diode. And now all of a sudden I had a speed of light link with all the bandwidth and reasonable dynamic range, and stochastic cooling worked in a recycler for many years before that was all over. Okay, so at the end here is how many bits are involved, because everybody's digitizing and things of that nature. Every bit is a factor of 2 in voltage. Okay, and so if I have 6 bits, then that's 2 to the 6th power, and that's my dynamic range. So you have what, 60, 2 to the 6th is what, 64? Or, yeah, 64 dB. And of course, typically that last bit, and you'll see it anytime you see a spec on a digitizing something router, it'll tell you effective bits, because that little last bit that's down in the noise, it's a noise bit. It's just flickering around, telling you. But if you do averaging, you can maybe squeak another bit out of it. So one of the things I'm asking in one of the spectrum manager labs is using the waveform generator. I'm not telling you to put out the maximum voltage. I just said go out to 50 millivolts, but you have an oscilloscope where you can see what the maximum voltage is, and then you can see what the noise floor is. And all of these things are generated by some lookup table, DAC something or other, when you got the waveform generators, and you'd be able to tell me how many bits it took to generate that. Okay, and so that's one of the questions on one of those things. But needing to get very high dynamic range, like on your, I don't know if people even use compact discs anymore. Compact discs has got a lot of capability in that most of them are 16 or 18 bits, which is a lot of dynamic range, but it's still nowhere near as good as your ears. Depends on how old you are. Your ears can easily have 120, 140 dB of dynamic range. As you get older, that diminishes quite a bit. And all these things with MP4s and everything else compacted, the signal noise gets much worse, and it depends on how good your ear is. And a lot of people still think that vinyl discs are better than DVDs and stuff like that. And so the only way to know that is you have to have a distortion analyzer, or you have a really good ear. Okay, so this now gets us through all the experiments. It gets us through all the experiments, I think, because the thing I'm going to talk about tomorrow is, maybe I wouldn't even talk about the VSA just because you guys have been using it already. I do have one talk left, which would be about an hour, which talks about putting a full system together and how all of the stuff we've been teaching here for the last few days, how it all comes together to become a system, and why you're doing this and why you're here. So it's just about lunchtime. Is an hour enough for you guys? Because I mean, now it's a 11:45. I don't eat lunch because there's more than enough food with breakfast and dinner. But we could, an hour and 15 minutes enough? Come back at 1 o'clock. Okay, and like I said, the first thing to want to do is to finish up if you can the spectrum analyzer basics, and then divide and conquer. I don't want people doing the noise figure thing until they've done at least matching or measured components, because I really want you to be. You did both matching and components?
No, we did the noise figure.
You did? How?
Noise figure? Wasn't that part of the?
No, I'm talking about measuring amplifier noise figure.
okay,
Yeah.
okay.
No, measuring the spectrum analyzer one, that's fine. But before you should hold off until you've had experience on network and spectrum analyzer before we do the amplifier business.
Yes. Yeah.